Okay, so when we look at this one, HCl went 1.88 times faster. I set this up as HCl is 1.88 times X divided by X because I don't know how fast the other halide goes. It's equal to the square root of the molecular weight over 36.5 grams per mole. That's the molar mass of HCl. So when we divide, we get 1.88 on the left, square that, and we get the molecular weight divided by 36.5. So rearranging, we get 129 grams per mole. And some of you had this upside down. You said X on the top and 1.88 X on the bottom, and you had these flipped around. You get the same answer because it doesn't matter which one is on top. It just matters that you have the right pairs together. So those are typical of the kind of problem you might see on the homework, on the quiz, or on the test. So now we'll start developing our idea about the ideal gas law. When we started talking about gases, we said all gases behave the same because they're in this constant random motion, they have no interaction with each other, and they all have the same kinetic energy at the same temperature. So all gases behave the same, and they approach ideal behavior. In the ideal gas law, we assume that all gases are behaving the same and that they follow the gas laws exactly. An ideal gas is imaginary. It doesn't exist. It's sort of like the ideal student. I imagine that I'll get some of these every semester. And occasionally I get some real students who approach ideal behavior. An ideal student would arrive to class on time every day and never miss. They would do everything I suggested. And they would ask probing, intelligent questions. They would email me questions about chemistry, but never send me emailed grades questions like, hey, you screwed up my grade. They would never send me emails like that. And I envision what it would be like with ideal students. Some of my students approach ideal behavior except at extreme pressure situations at the end of the semester and at midterm. Many students deviate from ideal behavior. Now, I imagine some of you are imagining what it would be like to have an ideal instructor. They would be charming and interesting and give everyone an A, right? So maybe some instructors approach ideal behavior also, but not exactly like that. So we can use the ideal gas law for real gases because most of the time, if we're not at high pressure and low temperature, the ideal gas law works. So we're going to talk about each of the variables in the ideal gas law. The ideal gas law, which is what most people remember, is PV equals nRT. And I've had a number of students over the years who say, oh yeah, that's the pervert law. I never thought of it that way, but if that helps you remember, go for it. So when we look at this, we're going to go through each of these variables and talk a little bit about them and look at their individual relationships. So P is the pressure, and we define pressure as force per unit area. And when we talk about this, we can use a lot of different units for pressure. We'll talk about that in just a minute. But we think about the atmospheric pressure, which is force per unit of area, air pushing on us all the time. We don't think about the air pushing on us. On Thursday when we lecture before, I'm going to show you a little demo. I didn't bring it tonight because I wasn't sure how much time we'd have. But we don't think about this, but you notice this air pressure when you go up in a plane or when you go down in the ocean, go down in deep water diving. When you go up in a plane, there's less atmospheric pressure. And your eardrum is vibrating because there's air inside your head and air outside your head, and your eardrum vibrates. When you go up in a plane, all of a sudden there's more air in your head than there is outside, and it pushes out on your eardrums and your ears hurt. So if you're a little baby, you start screaming, and when you scream on the plane, then that equalizes the pressure and you stop screaming. If you're an adult, they find that socially inappropriate. You can chew gum, yawn, blow your nose, and those things will help relieve that pressure. Then when the plane lands, the opposite happens. You now have less air in your head and more air in the atmosphere pushing in on your eardrums, and it makes your ears hurt. So you have to do the same thing to equalize that pressure. So that's the pressure. Now, when we think about this, it's not just the force. It depends on the area. Why is that funny?
Okay, my family were big on Star Wars.
Oh, so the force.
And instantly I'm like, the force?
It's the force. It's the force per area. So if you think about it, think about me. When I teach, I wear these shoes that are very supportive and reasonably comfortable for long periods of standing on concrete floors, right? And I have really exceptionally large feet. Someone told me once, they could have moved your ankle 3 inches and you could have been taller instead of having such big feet. And I thought, okay, that's just weird, but it's true. I do have really big feet for someone my height. So anyway, I wear these flat shoes that are very supportive, and I kind of measured how much surface area they take up. It's about 8 square inches. So if you take my approximate 60 kilogram mass, depending on the day, how much junk I'm eating, divided by this 8 square inches, I would have a force of about 7.5 kilograms per square inch. Now, as I'm wandering around, if somebody had their feet sticking out, and I just come up here and kind of step on your foot, what's going to happen? He's got his feet kind of stepping on. He's moving them. No, I'm not going to really step on your foot. If I just step on his foot, what's going to happen? He might not even say ow. He might just politely pull his foot back, right? Because is that going to cause him some excruciating pain if I'm just walking around here and I step on his foot? No, it's not. Have you ever had anyone step on your foot? I mean, in a crowded elevator or subway, and you usually don't make a fuss, you just move your foot, right? It would be unpleasant, but not particularly painful. So now imagine that I take off my everyday lecture shoes, and I strap on my Saturday night specials, my 4-inch spike heels. So now I'm teetering around, and I have trouble walking in these babies. Now, I step back, and I catch him in the instep with my spike heels. Does that feel the same as what Terry just felt? No. That is going to be extremely unpleasant, right? To the point of being painful. Now, I didn't gain any weight when I changed shoes. So the force is the same. But the area is considerably different. So now if we take that same 60 kilograms, and I tried to measure these, the area, it was less than 1/4 of a square inch, okay, these little spike shoes that I own. And so I'm estimating it's 1/4 of a square inch. So now it is 240 kilograms per square inch. That is like 32 times the pressure because I changed the area. Okay, I can use those to aerate the lawn in the spring. I can just go running out there and sink down in because there's so much force. Those are the shoes that mark up linoleum floors, right? And they make dents on the wood floor if I'm standing around long enough, which is why I don't wear them very much. And usually I only wear them for the first hour. Then I end up with something else on my feet. Okay, so that kind of gives you an idea of how it's force per area. We use a barometer to measure atmospheric pressure. We use a manometer to measure gas pressure inside of a vessel. And the barometer, we have one in the lab, and we'll be using it on Thursday for the activity. So we basically have a puddle of mercury, and inside is a long tube. This tube has been evacuated, so there's a vacuum in there, no air in there. And what happens is, as the air pushes down on this puddle of mercury, it causes the mercury to rise up in the barometer, not a thermometer. We don't have mercury thermometers anymore in the lab. We're not allowed to. It rises up, and we can measure the height of that column. And that is how we measure the atmospheric pressure. A manometer measures the pressure inside of a vessel. And so what we do is we attach some gas vessel to a U-shaped glass tube, and this is a manometer. And we put mercury in here, and then the gas pushes out, and we can use that to measure the pressure in the gas vessel.